ado, I'm gonna go ahead and start. Let's talk about alcohols today. All right, so whenever we talk about something, at least from alcohols right now, when we talk about a big chapter, it's going to be dissected into two parts. One would be the preparation of the functional group of interest, which is today it's going to be alcohols, and then we're going to talk about all the reactions that the functional group is going to go through. And this is the same format you're going to see for Orgo 2. If I do follow you up with you guys next year, expect to see the exact same layout, the same template. Okay, I got your last name. Thanks, Carlos. Yeah, so it's always important to know how we prepare stuff, because from there, sometimes, at least in your problem sets, you might see, preparation of an alcohol so that you can use the alcohol to do something with it, right? So it's always going to be two ways now. All right, so let's just do a little bit of a recap with alkenes. Who here remembers what hydroboration oxidation is? Say if I had this molecule, right, as a starting material, and I treated that with borane and THF, and then peroxides and sodium hydroxide, right? And what I get is an anti-Markovnikov alcohol. Very good. Okay, so this is anti-Markovnikov. All right, what about other reagents that you guys know as well? What are some other variations of borane? 9BBN, very good. 9BBN and THF, same thing. Peroxides. I can also use potassium hydroxide. I could also use B2H6 in diglyne. Okay, so these are alternate conditions. Know that they do all the same thing to give me an anti-Markovnikov alcohol addition. All right, oxymercuration, demercuration. Let's say I had this starting material. Okay, and I treated that with mercury acetate and water, and then reduce it down with sodium borohydride. What do I get? This is a Markovnikov addition. Very good. Okay. Markovnikov. And this, does it have any, what's the advantage of using hydroboration oxidation here? Why do we choose this over, let's say, acid catalyzed hydration? Yes, exactly. Because we don't want to have the carbocation rearranging. If we had this treated with the acid catalyzed hydration, what we'll get would not be the product that I just drew at the top, but rather it would be this here, right? Because of the carbocation rearrangement, it forms a more stable carbocation, and of course, benzoate carbocations are the most stable. So we know that that's not our desired product, right? Okay. All right. So we also talked about syn dihydroxylation. Say I had this molecule here. Right, and I treated that with osmium tetroxide. I'm just like zooming past all these right now because you guys should know what I'm talking about, right? So that when I go through the reaction later, when I start sodium borohydride, you guys, this is where I'll slow down. So this is a syn addition. Which is right here, right? What's another reaction condition that you might see to get me the same product? Potassium permanganate in cold conditions. Good. Okay, anti-dihydroxylation. Let's consider this molecule here. Okay, I have this. Can you name me the reagents? For an anti, it would be, it's a two-step process. Step one would be something we're going to talk about a lot on Sunday, epoxidation, right, in the presence of dichloromethane and MCPBA. And then we do a simple acidic workup. Okay, so as far as I'm concerned, I think you guys should know what's happening here so far. And of course, I feel like I knew what MCPBA is. It's a peroxy acid, right? And then this is the atom that gets donated. All right. So now this is where we're going to start talking about the actual new material based on what you've been exposed to with alcohol. So the first thing that we can do is to reduce carbonyls, right? Carbonyls are, of course, CO double bonds. You guys should know this by now. So what we are doing is to reduce a carbonyl into an alcohol of sorts. And one of the reagents that are really commonly used is sodium borohydride. And what it is it's a mild reducing agent. Okay. And with mild reducing agents, you can only reduce ketones into secondary alcohols and aldehydes into primary alcohols. Okay, let me just write into. Okay, I'll work through some examples later. Please take note that it's not strong enough. Okay, it's not strong enough to reduce esters and carboxylic acids. Okay, I'm gonna shorten this to Ca for future points. Okay, and then reactions carried out in the presence of an alcohol, methanol usually. Okay, there are other variations which I'll talk about later. Okay, so let's look at some examples. All right, so far is this speed okay with people who are attending? If I'm too fast, just let me know when to slow down. Okay, so let's look at this here. Okay, we have this with right. So when I have a ketone, right, we have a secondary alcohol that comes out as part of the product. Okay, and if we had, say, an aldehyde, then that's where we're going to get a primary alcohol. So this is secondary. And note that methanol is just a solvent here, which we will see later on why we have methanol. But you don't really put it into a two-step process. You just write it together. Okay, and what we get is a primary alcohol. Okay, we have a ketone, we have an aldehyde. What if I had this here? What would happen with this, the third starting material? You should be able to identify that this is an ester. And remember, esters are not, they're too strong, right? A sodium borohydride isn't strong enough to reduce it, so there is no reaction. Okay, basically what you get is the same starting molecule here. Okay, no reaction. All right, let's look at the mechanism, shall we? Okay, so I'm gonna use this example of benzaldehyde. Okay, treating it with sodium borohydride and methanol to give me this here, a phenol. Okay, this is the example I'm going to use. So as you have seen, boron, they behave a little bit differently, right? You have done 9BBN reactions, you've done borane, and usually it's a proton transfer from boron, right? And this is exactly what's happening here. So if we start with this, okay, I'm just going to put BH3 here with a negative charge, and then this hydrogen sticks out. This hydrogen here is going to attack carbonyl, right? Causing this oxygen to become a good nucleophile temporarily, right? But because it happens so fast, we don't usually put that in there. And then what happens is that it's going to attack borane. Okay, and what we have here is phenol with the oxygen here, because this is an aldehyde, right? And boron with hydrogen, and then H2 here, negative charge. Okay, so what we have is, right, exactly this. Okay, and you at this stage, you can either show like one more equivalent of your starting material coming in. I like to show at least two for this step. Okay, to give me this here. Okay, so this is H2 with a negative charge. And what you can do at this point is to just say repeat 2 times, right? You guys have seen this. You guys have seen this exactly with borane, right? But now you're just borane. You would just write repeat 3 times. Here you would show 2 and repeat 2 times. So you can write repeat 2 more times to get me. I'm just gonna write this. This is fine, writing R, because you're identifying this group as the R group, right? Because I mean you don't really need to show too many. So BOR3, but you have to show at least one left. Okay. Okay, so then the negative charge still stays there. Okay, so this is what we have, right? And then if you remember the 9BBN step, we would have the peroxide, right? The deprotonated peroxide attacking here. But we don't have it, right? Because our reagents are sodium borohydride and methanol. So this is where methanol is going to come in for the second part of the reaction. Okay, I'm going to bring methanol in. And what's going to happen is that, again, this is a continuous thing that's going on. So the lone pair from oxygen is going to grab the hydrogen here, kicking off this bond to the methoxy group. And then now the methoxy group has a temporary, it's just going to attack the boron, rather. Yeah, just want to make sure I'm not saying borane. Okay, so then what we have now is this here. Sorry, so once it happens, then this bond breaks off. Okay, so then what we have is we have our phenol plus the methoxy group that was attached earlier on to the original boron molecule. You see how this is just a proton exchange here, right? This is exactly what methanol does. It's really straightforward, really simple. And then at this point here, do you see that this is our product that we wanted, right? And then I would prefer if you just follow through with the whole reaction and you can just say, repeat 3 more times, right? Because 3 more equivalents of methanol is going to go in. And what's going to happen is that you would have your final product here plus boron, right? With how many methoxy groups? How do you know when the reaction ends? When all the ORs become O and E, right? Because we already have the methanol from the previous step, so it's going to be BOME 4 Ne plus. Okay, so this is how we know that this is the end of the reaction. Any questions before I move on? Okay, product. So yeah, this is a really common question on mechanisms. I usually see it in exams, but we'll see for this one. Yes, Yoshi, you're exactly right. You have 4. Technically, you would have 4 equivalents, but that's not really necessary. But as you can see, the steps are really similar, right? It's just a little bit of a different variation of it. Instead of water, you would have now methanol. Take note, you might see methanol as ethanol, isopropanol, and that's okay. It's just a variation. The only reason methanols or rather alcohols are there is to provide the hydrogen for the proton transfer. Okay, so yay, 1 reaction down, probably 9 more to go, so buckle up. All right, the next reagent we're going to talk about is lithium aluminum hydride. This is a big boy right here. Okay, it's a strong reducing agent. Okay, and my when I took Argo as a student, my professor called this the hammer because it's really strong. It's going to knock everything down. Okay, knocks all carbonyls into primary alcohols. Okay, let's look at some. Oh, sorry. All. Okay, now let me write it a little bit better because if you have a ketone, it doesn't reduce it to a primary alcohol. So it knocks all carbonyls, including carboxylate acid and esters. Okay, so if you had aldehydes, carboxylic acids, and esters. They get reduced into primary alcohols. And then if you had a ketone, it gets reduced to a secondary alcohol. Okay. Let's look at an example. If I had this right here, and I treated that with lithium aluminum hydride. Okay, usually this reaction is done in THF or diethyl ether. Either one that you write is fine. And it's a two-step process. We would also have an acidic workup step at the end. Okay, what you get is a complete reduction of the ester into a primary alcohol. Right here. Okay, if you had a carboxylic acid, it's the exact same thing. So let's look at a carboxylic acid. Okay, if I had lithium aluminum hydride, and let's just put, I usually use it in diethyl ether, around with THF. Okay, and what you get is again a primary alcohol right here. So basically you're just eliminating this carbonyl here. Okay. So it's pretty straightforward that so far, right? Want to look at the mechanism. Okay. The mechanism is somewhat similar to sodium borohydride as well, but instead of using boron, we are using aluminum right this time. And I'm gonna show you an example of this. Okay, using the same conditions, and I will show you how we're gonna get a primary alcohol. You could either just put water or you could just put H3O plus. It really doesn't matter. Let me just make this a slash. You could put both as well. That's fine. Okay, mechanism. So what we have is our starting material, right, with aluminum hydride right here. So like the one with sodium borohydride, same thing. This hydrogen here is going to attack the carbonyl, and then the oxygen from the carbonyl is going to connect itself to the aluminum atom, right? So what we have would be this here. Okay. Now at this stage here, this is where it's a little bit more interesting. We have a complete reduction of the carbonyl into an alcohol, right? So it means to say that we have to get rid of this ethoxy group or this OH group technically, because what we're doing is just converting the carbonyl into the alcohol. So you have to ask yourself, okay, how can I do that, right? I need to get rid of the methoxy group that's present right here. And this is how it's going to be done. So the methoxy group is now going to attack the aluminum atom. And in doing so, this bond is broken to form a new bond at the bottom here. Okay, let me draw out the products. So what you have is now benzaldehyde, okay, plus the methoxy now replaces the original starting material. Yes, it's H. Technically, it's H minus, so it will attack the carbonyl. Okay, so what you have is this now right here. Can you see that it replaced my starting material? So now we have this here, right? As the first product. And what's going to happen? Anyone wants to make a wild guess? What could possibly happen now? You repeat exactly. Yep, this hydrogen is now going to go up here, and then the carbonyl comes back down. Right here. Okay, and what we get is this right here. H, of course, there's a minus charge, hydrogen, the methoxy group that we originally had there, and then now we're going to have this guy here. Okay, yeah. Don't forget the two hydrogens here, okay? I'm not going to draw it out because I don't have space in there, but please note that they exist in there. Okay, and all you have to do right now is just show that it repeats itself again. This whole process repeats one time. The methoxy is gonna, another starting material is gonna come in, and then the methoxy is gonna do its thing. It's gonna get eventually to this stage here where you have two equivalent of your starting material and two equivalents of the methoxy ion. Okay, basically what you're doing, you see how it's pretty much similar to boron. So basically, how do you know when a mechanism stops? Is when you've saturated everything out. You replace all the hydrogens to the atom with your R groups. Okay, so when you are working with an ester, you should have two of the phenols and two of the ester components. Usually when they give you LiAlH4 reaction mechanisms, they like to give you esters. That's why I'm covering it now. So we know, okay, this has stopped already, right? So this is the end of step one, because there's nothing that we can do with this complex, right? We need something to come and activate it, right? What's going to come and activate it here is going to be water or acid, whichever you choose. I'm just going to use water. Okay, so water is going to be a source of hydrogen. Attack that one instead, so that I know what would happen here now would be this oxygen going into the aluminum. Because of that, I break off this bond here. Okay, and as a result, I get this here with aluminum with OH, and then okay, this is what you get basically. I don't have space to write it, but you can just show this step and that's fine. Okay, so what we have here is our product, as you can see, and this is where the reaction stops. Okay, so this step here is called the acidic workup. It's a really common term we use in organic chemistry. You're going to see it a lot in Orgo 2 as well, because technically this is what you guys are doing now is the first week of Orgo 2 next semester. So not too different from sodium borohydride. Yeah. Okay. So I have now. Let's see. Okay. Now we go on to something more fun. we talk about Grignard reagents. Now, Grignard reagents are a really big topic because why are Grignard reagents so powerful is because now you have another way to elongate a chain. When we talked about retrosynthesis, you guys remember I said, okay, for now you only have enough knowledge to know that we only had enough knowledge to know with alkynes, right, to make the chain longer, and ozonolysis kind of cuts it out into a shorter chain. But with Grignard reagents, we reduce a carbonyl into an alcohol while adding on a R group, right? So usually Grignard reagents come in the form of an R group attached to magnesium bromide, or in general, you might see it as any halogen, chlorine, bromine, and yeah, usually it's just chlorine and bromine. Okay, so let me just write this here. X could be any halogen. Okay, chlorine, bromine. Usually chlorine and bromine. I think I've seen iodine as well, but that's in a rare case. Okay, so what does it do is that it finds carbonyls, okay, and it reduces it down to alcohols. While adding R group. Okay, so we are definitely going to talk about the mechanism in a bit, but I'll just show you the general scheme of things. Okay, so one more thing to note is now you have another method of elongating chains. For retrosynthesis. Okay, so let's look at this example. So we right here we have a ketone, and let's say I'm adding ethyl magnesium bromide and diethyl ether. You could also use it in THF. Okay, and then step 2, you need to have an acidic workup. And what you get is this product here. So my benzo group is still there, but I'm adding an ethyl group while reducing my carbonyl into an alcohol. Okay. Of course, we have to look at the mechanism for that to understand what's going on. Okay, so I have my starting material right here. Right, and ethyl magnesium bromide. Okay, you have to kind of split the the reagent into two parts, the nucleophilic part and then the positively charged part. Okay, so this here is a really good nucleophile, and what nucleophiles do is that it goes on the quest to hunt for what? Most acidic proton. It goes and search for a good leaving group, or what? What do you guys remember about nucleophiles? Good, they search for electrophiles, right? And the electrophile that's hiding here, or rather is exposed, is the carbonyl, right? So it knocks out that double bond into this here. Now remember, you are adding on an R group, so this is where you need to show that there's an R group addition here, right? And then this is step 1 here, right? And step 2 is when you add water, what happens are an acid. Usually you would add acid. It's just ensuring that you protonate it. Okay. When you do that, what you get is the final product. Okay, really simple reaction. However, exceptions exist when you have an ester. So behavior with esters are different. Okay, so let's consider the molecule here. Okay, and if I added, let's say, methyl magnesium bromide, and then THF, do an acidic workup after. Oh yeah, acidic workup, great. Okay. What I'll get is this here. Let me change this to ethyl so that it's not so confusing. All right, so I would have my ethyl, my alcohol, and then my 2 added R groups. I'm adding 2 R groups now. 2 times addition. Why is that? Well, let's look at the mechanism. Okay, mechanism. Okay, so we start off with this, right? Methyl magnesium bromide, again, is going to be a nucleophile, which attacks the electrophilic center and gets me this here, right? So I'm adding a methyl group while having a negatively charged oxygen once I knock it off, right? Now, resonance is always really fast, remember? I hope you guys remember what resonance is. It's going to be fair game for your final. Resonance dictates that I would happen first before anything else can happen to me. So it forms a double bond. And when it forms a double bond here, which is a good leaving group? The methoxy group, right? The OMe. So then what you have here is a loss of leaving group. So that's kicked off, and you are back to now a ketone. And because you have another electrophilic center, what's going to happen is that the reaction is going to restart itself. It's going to come in again to attack the carbonyl. Okay. This time we're going to do a cross. Because that gets knocked out right now. So now I have a second addition of another methyl group. Right? And then the last step is just adding on the proton from water, or from an acid. Okay, and this just gives me the product. All right, any questions with esters? No questions? Okay. So Grignard reagents are really special because they take up such a big topic in alcohols. We are gonna consider the way they're being prepared. There are a few things that can happen with Grignard reagents. Okay, the first thing that happens that you can prepare a Grignard reagent from is from alkenes. So usually, if let's say they gave you this starting material, right? What you want to do first is to put depending on the question that they're asking you, but usually you would have bromine on the anti-Markovnikov site. So I'm going to add HBr and a peroxide because peroxides give me antimicrobial competition, right? Right here. Oops, that's not a oxygen, it's a Br. And then what you want to do, this is where, I mean, usually you should know how to get to here, right? Sometimes you might you might be lucky and they would just give you as a starting material. So all you have to do now is just insert magnesium, the magnesium atom in between the nucleophile, or rather, yeah, the nucleophile and the bromine atom. So how do we do that? We just add pure magnesium in THF. Or you could also use diethyl ether. And what you end up with is a Grignard reagent here. Okay, please take note to remember to account for Hoffman and Zaitsev rules if necessary. Okay, what mechanism? I didn't know like this was being taught to you guys this semester, so I would have probably to cover it then. Okay, so the mechanism is more, it's okay, how should I put this? Yeah, it's technically like a radical mechanism. I mean, you guys have done partial reductions with dissolving metal, right? It's pretty similar. So let's say I had a okay, let's just start with this. I have methyl here and bromine here. Okay, and I treat this with magnesium to give me this product here. Okay, so what happens is that when you have your starting material here, remember magnesium is in group 2, so it has 2 valence electrons. And what's going to happen is that it's going to transfer 1 electron to the molecule. Okay, not specific, not really specific to bromine, but this is usually just how we draw it. Okay, this is known as a single electron transfer. Okay, or SET for short. And what happens is that you're going to get a radical anion intermediate. Okay, so this is sort of like a, it's not really a, yeah, you can consider that as a transition state, where the entire molecule is now subjected to 1 extra electron on it, right here. Okay. And then what's going to happen is that you're going to have to try to insert the magnesium somehow, right? You have 1 electron in there, so okay, this is what's going to happen. Bromine is going to donate, it's going to push 1 electron out to form a bond with this electron. At the same time, it's going to push itself out of the molecule and give 1 electron to the phenyl group. Okay, so what we have here is a methyl, and with the 1 electron right here, with bromine as a nucleophile. Okay, this is where magnesium is going to come back in. Now remember, at this step, we dispelled magnesium, right? With just 1 electron, so it has a positive charge. Now magnesium with that 1 electron is going to come back and form a bond with the phenyl group, right? And what happens is you get this here. Because it still has only 1 bond, it will still be a plus charge, but it has no free radicals on it at all. Okay, and then the last step, of course, is bromine with the negative charge is going to come in and put itself at the end. So what you get is now your Grignard reagent. There you go. Okay, So it's a relatively simple mechanism. If they want to test something with radicals, you might see this on your final. Okay, just move this down. There we go. It's a regular error at the end because now bromine is a nucleophile, right? So everything now is just back to normal. The last step is where you show a regular arrow, and then at the start is always just a fish hook. All right, let's look at alkynes then. Okay, you can also prepare it from alkynes. Why? So let's consider the reaction, right? A terminal alkyne, rather a proton, a hydrogen proton at the terminal end of the alkyne has a pK of what? 25. Good, right? Which means that it's acidic enough for the Grignard reagent to deprotonate that. Okay. Deprotonate. Okay, let's look at an example. If I had this plus a terminal alkyne, right? What happens is that my alkyne would become the Grignard reagent now. So if you guys remember, we talked about bases, right? At the start when we taught you alkynes, one of the bases that can deprotonate it besides sodium amide was LDA or a Grignard reagent. So this is exactly what we're talking about. So what happens as a result of this is that it just gets liberated off as a gas. Okay, it just pushes out of the reaction mixture, which is let me see. Yeah. Okay. Let's look at another example just to be sure that you're understanding what's going on. So if every time you see something with less than 4 carbons, for example, right, with a Grignard, with any alkyne, rather a terminal one, okay, what you get is this here. Okay, negative charge here, positive charge, plus whatever is remaining here. So yeah, it's the same thing. Okay, everything out that comes out is a gas, which is why when we prepare Grignard reagents with alkynes, it's important that you have to use chains with less than 4 carbon atoms. Okay, this is an important note. Less than or equal to 4 carbon atoms, so that alkane can boil away. Okay, that's the whole reason why we want to do that. It just liberates off as a gas. So you might see such, for example, you might see methyl, or what I've been drawing, right? The vinyl. You could also have a simple alkene. You could have this as well. 1, 2, 3, 4. Oh, that's too much. So you could have butane or butene in this case. Stuff like that. As long as it's less than or equal to 4 carbon atoms. Okay. So Oops. Okay, let me see. Is there any mechanisms for this? No, it's your lucky day. We don't have mechanisms for alkynes. Okay, so we talked about alkenes. Now we talk about alkynes. And we are pretty much done here. All right, so whatever that you have attached to your Grignard reagent is going to end up boiling away. And then the Grignard reagent is going to attach itself to the alkyne. Okay, I was not going to talk about, oh, hang on. Sorry, yeah. There's one thing I do need you guys to take note. Okay, this is a really important concept that I could ask my Orgo 2 students today, and they would probably make this mistake, so please don't, is to remember that Grignard, my friend Mr. Grignard, okay, they are raging alcoholics. What does this mean? Okay, they will react with any hydroxy group within your molecule, okay, and therefore no reaction takes place. We'll see in a bit. We'll react with any hydroxy group, and therefore no reaction takes place. Okay, so I have a bit of a problematic friend. One of Naomi and her homies are too basic, and Grignard reagents have a drinking problem. Okay, why is that so? Because alcohols, right, the hydrogen atom from the alcohols are more acidic than a carbonyl. Okay, so of course, when it sees an alcohol, it just turns into a base and it deprotonates the hydroxy group instead of being a nucleophile attacking the electrophile. Okay, let's look at an example. Okay, so what happens here is that methyl magnesium bromide is going to be is also going to be a base in this case because it sees the alcohol atom, or rather the hydrogen atom from the alcohol, is going to deprotonate that right away. Okay, what's going to happen in the middle is this here. So now, instead of attacking the carbonyl, it becomes deprotonated, right? And then the best part is at step 2, when we give it an H3O plus solution, or rather when we give it a proton, what's going to happen is that it's just going to deprotonate. It's just going to protonate that. So therefore, what you get at the end, basically, as you can tell, is that no reaction took place. You're going to get back the same exact thing. Okay. The same thing happens with carboxylic acids. Okay, because you have an alcohol there. So if I had this, for example, benzaldehyde, sorry, not benzaldehyde, benzoic acid, and I treat that with ethyl magnesium bromide and THF, you can see I'm really not being consistent because it doesn't matter what you use. I just want you guys to get used to the idea that there might be more than one reagent. And then I do an acidic workup. Same thing is going to happen, right? Ethyl is going to be a good nucleophile, and it's just going to, sorry, a good base in this case, and it's going to deprotonate the hydrogen here instead of going for the carbonyl. What we get is this right here. And then we do an acidic workup, protonates, and then what I get is the exact same thing. Okay, so if you are going to work with a Grignard reagent, please remember to check. The first thing you do is to check your starting material for an alcohol. If you have an alcohol, forget about any reactions happening. Okay, good. Thank you for pointing that out, Yoshi. Yes, Jacqueline. So it doesn't even have a chance to get to the carbonyl. It just goes right to the alcohol. Because why? They are raging alcoholics. That's how I used to remember it. So I'm going to have to change this as well. Okay, there we go. So now we are good on the carbons. Then this one here is just going to be the same thing, no reaction. Okay, I'm going to talk about protecting it in a little bit. I was not going to mention lithium compounds, but because I saw a question on it come to your, I saw a question on it on your problem set, so I thought might as well just talk about it, just so that you know what's going on. Okay, a way to treat lithium compounds is to treat them as basic instead of being nucleophilic, right? So essentially, they are not Grignard reagents. Typically, okay, not Grignard reagents. Under what conditions? That's more of an Orgo 2 problem. So they behave more like bases. For example, you might see stuff like methyl lithium or butyl lithium. These are the two most common ones that you might see. And let's consider this case here. If I had a ketone here and I treated that with N-butyl lithium, you might think that this could probably happen, right? Does this make sense to you guys? Like technically, this is what you might think might happen at first? Or do you guys have other train of thoughts? No thoughts? Okay. So because this is not a nucleophile, it behaves as a base. It attacks the most acidic proton, and that is the proton next to the carbonyl, which you call the alpha carbon. Okay. So N-butyl lithium is gonna grab this proton here, and therefore an E2 reaction proceeds. It forms a double bond, and then it kicks it off. Okay, so what happens here is you would get this product instead. Okay, it deprotonates most acidic proton rather than a carbonyl. And why is that so? It's because of their behavior like bases. Okay, so the big concept here, so let me put the big picture. Okay, nucleophiles are electrophiles. And bases attack acids. basically. I'm just going to put it in quotation marks because technically I'm talking about the base will attack the most acidic proton. Okay, stuff like that. Yeah, so I've done the mechanism, but let's just go ahead and let me show you what happens when we do an acidic workup. Okay, so we know that under basic conditions, right, this hydrogen here gets deprotonated, elimination happens, and we get this here. Now, can anyone tell me where have you seen something like this before? Something like that looks pretty familiar, right? In a 9-BBN reaction or a oxymercuration of alkynes. This is known as the enolate, right? Remember we talked about keto-enol tautomerization. So what we have here is an enolate, and if you treat that with water or an acid, what's going to happen is that it's going to form back to itself, and then the alkene is now going to be the nucleophile deprotonating the acidic proton. So what we have here technically is the same thing. Okay, so just take note of that. The same thing happens with epoxides. You have to be careful because I think this was something that your problem set had. So just take note. Okay, so let's say I had this epoxide, and I treated that with methyl lithium and DHF. What you would get is the deprotonation of the most acidic proton, which is going to be right here. Methyl is going to come in, grab this, and then forms a double bond here, right? And then it will open up the epoxide. So what you get is, right here, and then the double bond that's across right here. Okay, and then if you treat that with an acidic solution of any sorts, you would just get your alcohol. Okay. So this is not something that you really have to take note, but just because it came out on your problem set, and if you guys see the answer and it seems a little bit different, you must be wondering what's going on. This is exactly it. Okay, butyl lithium compounds, or rather, sorry, alkyl lithium compounds, they behave more like bases. Okay, so which goes to say that, remember, it doesn't matter how complicated your molecule might be, right? If you had like a super, super complex molecule, and if you had like a Grignard reagent or say even n-butyl lithium, right? It doesn't matter because who will win in this case? Is all the see here all the carbonyls here? Are they gonna be good nucleophiles? Oh, sorry, are they gonna be attacked rather? No, right? Because it's either them or one little hydroxy boy right here. So this alcohol is the black sheep. It's the reason why, for example, if I have methyl magnesium bromide, it's gonna come and deprotonate this. It's just gonna ignore all the other carbonyls and go straight for the alcohol. Okay, so this is a really important concept that you need to know. Grignard reagents are raging alcoholics. Okay, so how do we get around that though? We have to protect alcohols, right? For those who were in lecture today, this is what you were taught before we went on to epoxides. So we need to protect alcohols if we were to treat that with a strong, a pretty strong base, correct? So let's see here. I have this reagent with, and if I treated that with methyl magnesium bromide and diethyl ether, then do an acidic workup. Okay, what would be the outcome of this reaction? It will, yeah, it will be the same. There's no reaction, right? As we talked about, because of this alcohol here. So what we have to do is to protect it. Need to protect alcohol before conducting a Grignard reagent. Okay, and how do we protect alcohols? We use something called trimethyl silyl chloride. Okay, we abbreviate it as TMSCl for short, and it looks like this. Okay, let me just shift this to the side. So you don't need to know the mechanism for this, thank goodness. If I have the same starting material as I was working with earlier, and I treated that with TMSCl, you could use pyridine or any organic base. You might see variations such as triethylamine, right? And all you need to remember is that the OH now becomes OSIMe3. Or you could just abbreviate this as TMS. You could write TMS and that's fine. So now if I use my protected molecule with my methyl magnesium bromide from earlier, now my this Grignard reagent can attack my carbonyl because it doesn't do anything with an ether, right? It attacks my carbonyl to give me my product, and because I'm adding methyl, so I would have this reaction going on. Okay, I would be able to successfully form my product, and then I would just have to end off the reaction by deprotecting the alcohol, which means I need to remove the trimethyl silyl chloride part and just revert that back into an alcohol. So what are we going to use? We are going to deprotect alcohols with TBAF. You might see cesium fluoride as well. You could use either one of them. It's fine. So if I had the same thing here, right, and I'd use just TBAF in water, then what you get is now my original alcohol that was protected earlier on. Okay, what is TBAF? Okay, so TBAF is basically a good source of fluoride ions. Via this reagent here. Okay, so fluorine and silicon, they have a really good affinity to each other. That's why we would use that to rip it out and then put it back with the hydrogen in there. Okay, I'm just gonna write here, no need to know mechanism. It's a good thing. Okay, now we're gonna talk about oxidation, right? Okay, so we are pretty much done with preparing alcohols, right? Now we're going to talk about the reactions that alcohols can go through, right? And one of the major steps that usually people do with alcohols is to bring it up into a ketone. So we went down, now we're going back up, okay? Let's see, we had, for example, okay, when we had this here, right? What happened when we treated that with sodium borohydride? What we ended up with was a secondary alcohol. Okay, and then if we were to go back to the ketone that we started off with, okay, this is what we're going to talk about. Basically, the oxidation process here. I'm going to use this notation a lot because there are many ways you can oxidize an alcohol into a ketone. Okay, so usually there might be more than one answer. You might ask me, oh, could I use PDC instead of PCC? Usually when I give solutions, I would just put this bracket with the O in there. And that just tells you, as long as you know the concept of oxidation, any reagent you provide will give you the full credit. Okay, so the first one we're going to talk about is Jones oxidation. So I'm going to use the same example from before. Okay, this is a secondary alcohol. So what I get, if I oxidize it with Na2Cr2O7, you might see K2Cr2O7. These are all the same thing. You might even see CrO3, right? Usually done with water and acid. Okay, what you get would be a ketone because you're working with a secondary alcohol. If you had a primary alcohol, no, I will not talk about that later. Let's say if you had something benzylic, right? You're gonna slice off everything here because you have an available hydrogen here. This is going to be the source that gives everything that makes the whole aromatic ring basically. Sorry, what am I talking about? The benzyl group become a carboxylic acid. So same conditions. What you end up with would just be this here. Okay, it must be benzylic. Take note. Okay, and then if you had, for example, terbutyl group though, if you had a terbutyl, there would not be any reactions at all. Okay. Because hydrogen is not available at benzyl site. Available at benzylic site. Okay. Let's see. If you had an primary alcohol, right? Now you might think, okay, with a primary alcohol, I could oxidize it into an aldehyde, but that is not really the case. Okay, you don't really get the aldehyde. What happens is that you would get a carboxylic acid right away with Jones reagent. Okay, and the reason this happens is because Jones reagent is harsh. it's hard to isolate the aldehyde, and it just goes straight into a carboxylic acid. And this only happens with Jones reagent. Okay, I'm just gonna write difficult to isolate an aldehyde from primary alcohols. So it just goes straight to carboxylic acid. Okay, so how do we get around this? We'll talk about it later in the next two reagents, but first I want to consider the mechanism. Okay, we have the mechanism. So, all right, the easiest way to think about it is by using this instead of CrO3. Okay, because I don't see a need for you guys to overcomplicate things. I'll just write it later. But let's just use the sodium dichromate. Okay. So Cr2O7 looks like this. And if you had your starting material, which is your primary alcohol, right, I'm going to show you the mechanism for the primary alcohol. Okay, so what happens here is that alcohol, or rather the oxygen, is going to insert itself into chromium. Okay, and then it causes one of the double bonds to be broken. So what you get, okay, I'm gonna go really slowly on this, so if you're ahead, just bear with me, because I just want to make sure you guys are understanding what's happening here. Okay, so now the one that got kicked off becomes negatively charged. This one here also becomes negatively charged, no change. We have a double bond here, and then of course we have this one here. Okay. And then what's going to happen is that you are going to form a double bond again. Doesn't matter which one, right? Remember, resonance is always faster. So once you have that going on, this becomes a leaving group. It gets knocked out. And what you have is this right here. Right? And then the molecule that you knocked out earlier, let me see. It's going to come back in to take away the extra hydrogen. Right? I forgot a plus charge here. So the leaving group that you knocked out is going to come back. Where is it? Oh, okay, it's right here. Let me just draw it. Okay, and it's going to take away this proton here. Then you're going to be left with this right here. Okay, so now this is now neutrally charged. There is no more plus charge, and yeah, okay, so very good. what we have now is sort of good, but I need you guys to pay attention to this hydrogen here. Okay, let me see. Let me draw this here. Okay, whoops, sorry. All right, so this carbonyl here is gonna grab this proton, and as a result, when you have a proton that's being taken away, right, you would naturally form a double bond somewhere, right? And where's this double bond gonna be formed? Of course, it has to be formed with the carbonyl here. Why? Because you want to knock out this bond, and then what we get is this molecule here. Oh, okay, I'm sorry. I think I made a mistake. I forgot to put hydrogens here. And then this should have a hydrogen here, so it's an alcohol. And then it gets knocked out. One of them has a hydroxy group. Then this has a hydroxy group. Okay, sorry about that. All right. The arrow for the leaving group is from bond to bond. Yes. So the okay, let me redraw this arrow here just to show you in detail what's going on a molecular level. Okay, so the oxygen here is gonna grab the proton. Proton forms a double bond once it gets taken away, right? And then this bond to chromium is broken. Okay, I hope that kind of cleared things up a little bit. And what you have as a result would be this. You would have an aldehyde. So this is where you know you're doing things right. When you get the aldehyde, you will, this is sort of your first checkpoint here, okay? All right, let's see. Yeah, you get this plus this chromium intermediate here. So you would have two carbonyls with one alcohol. Oh, sorry, two alcohols with one carbonyl. All right, so now you have your aldehyde intermediate. Let me just put this here so you guys know. Okay, I'll get to that. Okay, so what's going to happen now is that you are, remember this is a three-step process, right? You have your Jones reagent, sulfuric acid, and then water. Okay, so what you want to do right now is, just in case I don't have space, probably. Okay, is that now that you're under acidic conditions, what happens is that your this oxygen here is going to be a better nucleophile in general. So find sulfuric acid. It's going to grab a proton here. Okay, let me just draw this right here. And then this is a positive charge. And now water is a good nucleophile. In this case, it's now going to come in and attack the carbonyl. So you're going to get this intermediate here. Methyl, hydrogen, alcohol, and OH2+. And then early on, when you deprotonated the sulfuric acid, it's going to come back for revenge to give me this here. Okay, so now that you know this is formed, right? It's gonna go through the same exact route as you started with. In lecture, you guys were told, okay, this just repeats from the first step, but I've decided to go through the entire thing anyway. So please bear with me. I'll try my best to go at a reasonable pace. All right, so let's bring in back one more molecule of our starting material. Sorry, not starting material, the reagent, rather. Okay, and the same exact thing is going to happen as from before. Any one of the alcohols, doesn't matter which one you choose. Okay, it's going to come in and attack the chromium atom and then kicks off a single bond in there. Then okay, it's going to look like this. I'll try to draw it as clearly as I can. So let me know if you're lost with any part. So we have and then I have a hydrogen here with a positive charge. Okay, all right. Now, as before, see what happened here? This is going to form back into a double bond. And then kick off the entire leaving group here, right? Same thing, forms a double bond. Goodbye. Right here, you would have is this here. So now you have 2 carbonyls and then 1 alcohol with it, with methyl here and hydrogen here. Okay. No prizes for guessing what happens next, because you should know that the leaving group has a negative charge right here, right? So it's going to come back and attack this proton. Okay, grabs off that proton to give this here. I'm not going to draw the second product because this one is the exact same thing here. Okay. All right. Now, so from here, how did we go? So this is now sort of like where you might be stuck at, right? But remember, something has to come and take it, right? So this carbonyl here, let me use the bottom one. Let me use the bottom one here. Okay, this carbonyl is going to grab this hydrogen. By doing so, it's going to form a double bond with the carbonyl, knocking this out to give me this here, which is basically my carboxylic acid, actually. So then I know this is the end of my reaction. Plus, we had what we've always been making as a byproduct is going to be the same here. Okay, so this is the product. Oops. And all right, so the arrow for the leaving group is from bond to bond in the second step. No, not from bond to bond. What I'm trying to show here is that this bond is being broken away from the chromium compound. Okay, you're not forming a bond with it. All right, if you had chromium CrO3, for example, let me just put the mechanism for CrO3. Usually that it's a little bit different because you have to make, so you guys know what CrO3 looks like, right? It's just this here. If you had this, then you would have to make it similar to what we started with here by adding the sulfuric acid. So H2SO4 is going to come in as a reagent here. Okay, and what happen is that it's going to grab this proton. So remember, ketones under acidic conditions are really good nucleophiles. It breaks off this bond. So you're going to have this and this here. Okay, and then the remaining, whatever is remaining from your sulfuric acid, that's a negative charge here. It's going to come in and attack the chromium to give me this here. So now I would have 1, 2, 3. This here. So now it's now pretty similar to what we started off with when we talked about the mechanism, and everything else is just the same from here. I'm not gonna do the reaction mechanism for this because, well, like I said, really similar. The only thing that happens is this group will leave here. Okay. If they ask this on the exam, I honestly doubt they would, but if they did, they might ask you to draw it from the aldehyde or to the aldehyde. I don't think they're going to ask you to draw the entire mechanism out because, as you can see, it's really long. But it's good to know just in case. So this mechanism is for oxidation using Jones reagent. Okay, everything I've been talking about here so far is we're still on Jones reagent. And right now I'm going to move on to PDC and PCC. Okay, pyridinium dichromate or chlorochromate, depending on what you have. So remember, what's a limitation of Jones reagent? Anyone here remembers? It's to, yeah, you will always over-oxidize it. You can never isolate an aldehyde. So one way to get an aldehyde from a primary alcohol is to use something moderate, right? And this is where PCC or PDC comes in. So if I had a phenol, oh, not a phenol, sorry. If I had this here, okay, and I treat that with PCC or PDC, and this happens in the presence of pyridine, what you get is the aldehyde. Okay. You would not, and it just stops here. You won't have it going all the way to a carboxylate acid. Okay, so what's PCC? You guys need to know this, okay? PCC, chlorochromate, right? So it has to have a chlorine at some point, and everything else just remains pretty much the same, except that now the one of the oxygen is negatively charged. How do we balance that out? We use pyridine. Okay, so this is PCC. And then PDC, dichromate. So you're gonna have to repeat this unit, but instead of chlorine, you're going to put 2 of them together, right? So you would get this here. And then you're going to have 2 equivalents of pyridine because you have 2 negative charge. Okay, so depending on what you get, you need to know how they look like. Now, I need to draw your attention to the leaving groups. If you have, because you're going to kick out a leaving group, right? In PCC, the atom that leaves is the chlorine atom. In PDC, it's this entire molecule here. Okay, it's just going to leave. So it doesn't matter because you don't need to be afraid if you get PDC. Just know that one leaving group is just way bigger than the other. Okay. So anyone wants to guess what comes after this part? What are we going to talk about now? Starts with M, ends with mechanism. What is what's a reaction without mechanisms, right? Okay, same thing. Let's start with this here. From the example that I gave. Okay. Again, every time you have a chromium compound, the alcohol, your starting material is going to attack it, and it's going to break off one of the double bonds in carbonyl. Right, and what you get is this right here. Okay, and then resonance is going to dictate that, you know, my formation of a carbonyl is going to be really fast, almost instantaneous. So I form a double bond, and remember when I highlighted the leaving group for PCC, what leaves? Chlorine, right? Chlorine leaves, and you get this molecule here. Okay, now remember, every time you have the positive charge on the oxygen, you need to get rid of that hydrogen. That's also one of the key steps. Thankfully, though, you have something negatively charged here, so that's just naturally going to go for that. And you restore peace around that oxygen bond. So now the hydrogen ends up on the negatively charged oxygen. Okay. Of course, you dispel chloride ions. Don't really need to care about that. But what happens now is that, remember, you have implicit hydrogens here, right? Your carbonyl, or rather the oxygen from the ketone, or the double bonded oxygen, is going to depronate this here, forming a double bond right here, and breaking off the bond from chromium. Okay, and what you get is now this here. Okay, as you can see, there's a pattern from the Jones reagent, but this is way simpler. So in the exam, you might actually get, I would think you might have a higher chance of getting this in the exam. Okay, do note that some literature or some textbooks have an alternative set of conditions. They might argue that the chloride that was dispelled earlier from the leaving group, right, as a leaving group, is going to attack this proton here. So I don't know if that's acceptable if you choose to do that, or if you saw that, but I would just say stick it with whatever you have learned in class. That's always a safer option. So just follow the arrows in pink. Okay, so that is it for PCC and PDC. We are down to our last slide. Fantastic. Well, yeah, I'm just done with one last reaction, and then we'll continue ethers on Sunday. All right. So the last one that we have is Swin oxidation. Okay. The reason why Swin oxidation came about was because chromium compounds are like to do with their waste. It's pretty nasty. It's it's like a transition metal. It's not as clean. So they looked at other ways that you could oxidize something without using such poisonous and toxic reagents, right? Okay, Swin oxidation is one of them, and it came at a price. The price being that it stings like crazy because you're producing dimethyl sulfide, DMS. So let me use the same reaction condition. We have this. Now the conditions are oxalochloride and DMSO. This is dimethyl sulfoxide. If you guys can remember what that is. And then step 2 is triethylamine and dichloromethane. And usually this reaction is being carried out. You might see this in your problem set, but in Argo 2 problem sets, they're really common. So it starts at negative 70 degrees, and you just take it up to room temperature. And what you have here is basically an aldehyde. If you had a secondary alcohol, then you would have a ketone. All right, so remember oxalochloride. Okay, is this right here. You might see it expressed as COCl2. It's the same thing. Basically, that's just how you empirically express it. Dimethyl sulfoxide is DMSO. Triethylamine, you guys should know what that is, and you don't need to know what CH2Cl2 does because that's just a solvent here. Okay. Again, our magic M word comes out. But well done. This is the last mechanism for tonight. Okay. But you need to know what DMS looks like, right? Dimethyl sulfoxide is this right here. It can undergo resonance to form this here. Okay, and this is where we're going to start, this part here, the less stable contributor. What's going to do? Well, the hint lies in the reagent set. You have to use oxalochloride first, right? So this is where you're going to come in. And what's going to do? The oxygen is going to go straight and act as a carbonyl. Go straight for the carbonyl to give me this. Okay, and then similarly, resonance is gonna call it back down to form a double bond, kicking off this as a leaving group to give me this here. Okay, so I take away the chlorine. It's gone. Goodbye. Then this chlorine is going to come back. Okay, remember, every time you kick something off, it's probably not happy about it, so it's going to come back for revenge and attack the positively charged sulfur atom, knocking this out, right? Okay, at the same time, what happens is that you're going to form a bond here, and you're going to kick off this here and kick off the chlorine. You don't really need to know this part of the air pushing mechanism. It really doesn't matter if you don't know it in detail, because what you need to at least show is that you're gonna liberate CO2 gas, you're gonna liberate carbon monoxide, and you're gonna liberate one more molecule, one more atom of the chloride ion. Okay, so all these gases except for the chloride boil away. They're just gases, right? And what you're left with, which is now gonna be the next key step, is your chlorosulfonium ion. Okay, let me just write this here. This is your chlorosulfonium ion. Okay, this is a major step, one of these steps here in this swirling reaction. So once you get here, you know, okay, you are pretty much on the right track. Let me just rewrite this here. Okay, now with this, what might happen next? You might think, right? What else have we not used? So we've used this. We have used this. Now we have to bring in our starting material. Starting material comes in. Same deal. Attacks the sulfur. Okay, and what happens is that this chlorine gets kicked off. Okay, and how do you think the the additional hydrogen is going to get deprotonated? Well, you might think it's a chloride ion, but it's not. This is now where you're going to use triethylamine, right? Triethylamine comes in, grabs this hydrogen here, and you don't need to show what comes out of it. I would expect you to know that for Argo 2, but I don't think you need to know that for Argo 1. Okay, so now this is a happy molecule here. Now we got to figure out how are we gonna form the double bond, right? It doesn't seem like we can form a double bond with anything, but the key lies with the methyl. It's hiding in here. So let me draw this as a CH3 group so that you can see what's happening. Okay, with this CH3 group, another molecule, another equivalent of triethylamine is going to come in, depronate this hydrogen atom here. Okay, so that I get a very unhappy king. Those of you who've been to my resonance review, you should know what I'm talking about, right? When your king has a negative charge, when carbon has a negative charge, it's unhappy. It's really, really unhappy, right? That's why it's a good nucleophile like that. So what's it going to try to do is to restore itself back into its full octet form. And what we're going to do here is to just grab this and attack the hydrogen here, forming the double bond, and then breaking off from the dimethyl sulfide, basically. So this is where dimethyl sulfide comes in, and you know it's going to be super smelly, and therefore your reaction is conclusive from here. So you're just going to put this here. You get my aldehyde plus DMS, which is the bad odor of the reaction. Okay, remember DMS? When have you seen a reaction using DMS? Are you sure SN2? That's DMF, right? DMS, something with ozone, right? Ozonolysis. Use dimethyl sulfide on alkenes when you have an ozonolysis reaction. But basically, this is what you're doing here. Okay. So, Jacqueline, your question was, how does the byproduct have two OH groups? That is from the previous one. All right. So already with the chromium, this has one OH here, right? So it's going to grab another hydrogen, but doing so, right, it grabs here, forms a double bond here, knocks it out from the chromium. But technically, what I did not show is that this double bond is knocked out so that it becomes the other OH. We usually don't show that. Okay. All right. Is there any other questions? Because it's 8:37 already. Pretty much just 7 minutes over 2 hours. I don't think you guys have the capacity for any more mechanisms, which I'm going to talk about on Sunday anyway. So anyone here has any issues? There were a lot of reaction mechanisms, right? Abdul, as you can see, we have done PCC, PDC, Jones, CERN, Grignard's, butyl lithium compounds. I will be uploading these notes as soon as I clean them up, so you can expect them probably by in an hour or two, maybe even lesser. Additionally, I am going to open the registration form for this Sunday for epoxides and ethers technically. So bring this with you if you're coming on Sunday, okay?